In this video, we introduce GUESS, a generative modeling approach that exploits variational encoding and adversarial learning for inferring missing knowledge for mobile robots. The key idea is very intuitive. As humans, we are able to generalize and operate in partial observability. We can imagine and extend knowledge beyond our sensory horizon. For example, can you guess what's on the other side of this environment? As a matter of fact, we can. We can estimate the size of the room, and just by looking at a few pixels, we can guess that there is a table. Then, when we navigate the environment, we have the possibility to confirm and adjust our previous estimates. Hence, the aim of this work is to provide robots with such an ability. Given the robot operating in an environment, our objective is to collect sensory observation and formalize such observation as past experience, and expand the sensory horizon by predicting the next observation that will be perceived by the robot. Such a skill allows a robot to predict, to guess, future observation and hence to better reason and act in unknown and partially observable environments. There are different approaches that attempt to extend the robot perception and knowledge about the environment. However, either they rely on pre-trained models or they explore geometrical characteristics of known landmarks of the scenario. In contrast to such approaches, GUESS is able to learn environmental landmarks without prior knowledge and to update its model in real time and online. Such a feature gives the possibility to operate in dynamic and unknown environments, which is fundamental in robotics. GUESS has a very flexible architecture that is agnostic to the state of observation, hence it can be used in any domain and application. In this work we consider the case of 2D laser scans coming from a range sensor. GUESS is an iterative algorithm that at each time steps exploits t time correlated input observations, couples them with velocity commands, linear and angular velocity, and predicts the observation that the robot is going to perceive at t prime time steps in the future. We configure the algorithm to run at 1 Hz, which means that if, for example, we configure t and t prime to be 8 and 10 seconds respectively, then GUESS will consider a stream of data lasting 8 seconds to estimate the sensor observation that will be perceived after 10 seconds. To learn the distribution of robot observations and to generate laser scans, we exploit generative adversarial networks. However, GANs might be sample inefficient and require long training sessions to learn the target distribution. Moreover, a factor that determines the accuracy in generating new samples is the state dimensionality of the input. To overcome such issues and reduce the state dimensionality to be capable of using adversarial networks with reduced training samples, we exploit variational encoding. Such encoders are particularly suitable for our needs. In fact, variational encoders learn a latent, more compact, yet informative representation of the input data. In particular, a BI is trained by minimizing a two-component loss, a reconstruction loss that quantifies how good the sample is being reconstructed, and a Kullback-Leibler Ventures loss that intuitively encourages the encoder to distribute all encodings evenly around the center of the latent space, generating a continuous distribution of features, which is fundamental to be able to sample from the latent space. So in this slide, we can see the complete GUESS architecture that features both a BI and a GAN. The former is used to reduce the state dimensionality and make our solution practical in robotics use cases, while the latter is used to collect latent samples, couple them with velocity commands, and generate future observation, which will be decoded by the decoded part of the variational encoder. Specifically, in our experiments, we receive as input a laser scan composed by 512 beams, and we can efficiently map such an input in a latent space which is dimensionality of 6C. In this slide, we can see the accuracy of the BI in reconstructed laser scans. Original laser scans are shown in red, while reconstructions are shown in orange. In this slide instead, we show the generation of the laser scans that the robot is going to perceive in the future. In this experiment, we buffer a stream of 8 seconds to generate laser scans perceived after 5 seconds. The balloons represented the corridor, a large room, and a narrow passage. The red line is the original laser scan, the orange is the reconstructed target scan that is used as a ground truth in the GAN training, and the blue line is the generated guessed scan. Intuitively, it is important to notice that the accuracy in the generation is strictly conditioned by the quality of the embedded latent features, which suggests that, at the moment, we should focus on improving the BI performance in order to gain more fidelity in the GUESS scans. Summarizing, GUESS is an online real-time implementation that iteratively refines its model to predict future observation of a mobile robot operating in unknown environments. Our goal is to expand the robot sensory horizon to support and improve planning for robot actions. However, our approach still presents limitations in prediction accuracy, which is going to be tackled in the next steps of the development of GUESS.